Welcome to Module 3, where we're going to talk about creating your own distributed autonomy projects. In this talk, we're going to focus on a project configuration tool called the GPC to create and manage portable GAMS Madara projects. Basically, this talk is going to cover what to do after GAMS Madara is installed in your system in order to create your own GAMS-enabled projects. In this talk, we're going to learn how to create our initial project, how to compile a GAMS project, how to generate your own simulations for quadcopters, boats, and other platforms in VREP, and how to generate custom threading, algorithm, platform, and networking transports. Before we get into the technical details of what you can generate, let's talk about the overview and understand how gpc.pl works. gpc.pl generates a project, a custom user application with a controller. This controller interfaces with any number of threads, algorithms, platforms, and transports that you generate from the GPC. So let's go ahead and generate a new GAMS project. It's a lot easier than it sounds. All you have to do is call gpc.pl with any path, and in this case I called it project root/tutorial1, but you can put it anywhere, your home directory, inside of your own projects directory, anywhere you'd like to generate things. Providing only path information is the bare minimum project creation process. It'll generate a bin directory for your future controller, it'll generate a sim directory with a basic sim for VREP, and also source directories for algorithms, platforms, threads, and transports that you might add later.
Okay, so for the first tutorial, what we're going to do is try to create a simulation, show you how easy it is to set it up, and then run it. So you can see that in our Deck 3 here on 3.5, that's Module 3, Slide 5, we're going to be creating a new tutorial called Tutorial 1 in Project Root. Now to set up Project Root, you essentially need to create a directory somewhere that you want to put things, and where I'm going to put them is inside of home/tutorials. So I'm going to say export project root equals, and I'm going to say $home/tutorials. Now if you don't have this directory created yet, what you need to do is say make dir tutorials inside of your home directory. In this case I already have that existing, but once you have this variable set up and once you have your directory created, now you can actually copy and paste this line from your slide notes. Just press enter and it should run. It's not going to print out anything. That means it's successful. It has created the tutorial 1 directory, and what we're going to do is we're going to copy this next thing, which should run the simulation, to the terminal as well. It'll launch up VREP. This is a simulation environment, and it will start populating the environment with squares of environment and also a quadcopter. Now the quadcopter is going to appear very small on here. You can zoom in obviously to take a look at it, but you can see that we essentially have a quadcopter here in the very center, and we're very zoomed out. But that's all you need to do to create your first simulation in the GAMS infrastructure. Alright, for the next tutorial, we're going to actually create 5 distributed agents that are randomized around the screen, and then we're going to sim that. So, let's go ahead and follow the slide notes here. It says to change directory into the project root tutorial 1 directory. This is just so that we don't have to keep saying --path, it just makes things simpler to add new arguments. We're going to change the logging levels here to 1 and 1, which means only warnings and errors for GAMS and Madara messages, and then we are going to configure 5 agents randomly distributed around the area. So we're just copying and pasting these, and last but not least, we are going to start up VREP and simulate the changes that we made. So you can see that we've got 5 drones here. You can see the quadcopters being created here, and we've got a new environment for them to play in. Now once we create algorithms, we'll be able to move these around the screen, but for now all they're doing is being initialized into random locations in your environment. All right, next we're going to make those 5 agents not randomized anymore around the area, but actually distributed in a very organized manner in the environment space. So let's go ahead and clear this out. We are back in the directory where tutorial 1 is, and instead of doing what we did before, we're going to just make them distributed. So we're just passing the distributed argument to the GPC. I'm just going to copy and paste this from slide notes. Then we're going to again run the action vrep sem commands and see what it looks like. So you can see, once we start being able to drag this, you can see that there are 5 agents again, but this time they're actually spaced evenly amongst the environment, which may help if we're doing things like collision avoidance algorithms and things of nature to get them in a good position where they're not on top of each other. That's all there is to it, to getting your distributed agents in place.
So let's change the simulation we generated to include 2 groups of agents. You're not going to see any difference in the simulation we generate here, but this is a logical grouping of agents to show you how you can actually form teams in your agent systems. So here we call GPC with group attackers and group defenders, and we give it a range of agents to do from 0 to 1 and 2 to 4. Then we call the action.sh script with vrep and sim. This will actually launch vrep and sim the agents for us. These groups and their memberships will be available to any algorithms you design later. Memberships are placed in the sim common.mf file, and groups can be fixed or dynamic, meaning people can come and go out of groups later if you'd like. The next thing people often like to do is to isolate their simulation from others. There are 2 different ways to do that. The first way we'll cover is using a domain. A domain is essentially a partition of the network that is yours. So in this case, I'm setting a domain of James E so that anytime I want to run agents, only the James E ones will talk together. Simulations by default use the same multicast IP address. This means that if your coworker is on the same network that you're on, both of your simulations will talk to each other, and potentially you won't have the right algorithm execution. A domain is a logical partition of the network transport to allow you to have the same multicast IP, but each of you is a separate entity in the network and traffic. Traffic from other simulations will still arrive, but everyone else's knowledge will not be applied to your simulation. There are more effective ways to isolate your simulation from others. For instance, you can use a different networking transport. If you remember, the Madara technology that's underneath GAMS has a networking transport that you can configure with various UDP transports. You can also use DDS or 0MQ. Here we're going to set a multicast IP of 239.100.540. This will put us on a completely different multicast space so that other people's knowledge will not even reach us, and we won't have to make any kind of distinctions with a domain. After that, you simply launch the simulation with action.sh using vrep and sim, and everything should work. Any simulation that's generated by default will use the multicast endpoint 239.255.0.1. We can choose any random multicast IP to effectively isolate ourselves from anyone else using the network. You can also switch to any other transport, including UDP, DDS, or 0MQ, to completely isolate yourself from other people performing simulations in your network. Next, let's talk about the controller extension process. Controllers are regenerated whenever you create new threads, algorithms, platforms, or transports. Projects will also be regenerated whenever new files or libraries are added or removed. You might do this whenever you want to include a new external library that is important for, say, image processing or something like that in your project. Next, let's talk about how the controller interacts with algorithms and platforms in the GAMS system. A controller executes algorithms and platforms in a MAPE loop. That's monitor, analyze, plan, and execute. The MAPE process in GAMS is a very ordered process. First, the system analyzes the environment to see if anything needs to change regarding the algorithm that needs to be executed, or the platform itself needs to be changed to some reduced mode, for instance. Then the platform calls its sense method, which is the monitor phase of the MAPE loop, to see what has changed in the environment around it. After that, the algorithm and platform get to run an analyze phase, where they get to process the world state and figure out what they're going to do next. Then the algorithm runs a plan function and an execute function that you create in your application. There are 2 important quality of service properties that are attached to the MAPE process itself. The first one is the run hertz. Run hertz is how fast you want the MAPE loop to run. This is important because many sensors need to run at high frequencies, such as 30 hertz or 60 hertz, in order to process their state. However, you probably want a different quality of service for how often you're sending updates over the network. GAMS provides this through what's called the send hertz. The send hertz and run hertz can be very different values to allow you to not overwhelm your network with emergent behaviors and emergent communications that thrash the network underneath. Next, let's talk about adding threads and other components to your GPC project. Here we open a Linux terminal and we create a couple of things. First, we create 2 new threads called sense and analyze, which are supposedly going to be a persistent thread that's running all the time, and we place them in source threads. We also create a new algorithm called intelligent ISR, which will be placed in the source algorithms directory. These new generated threads and algorithms have null implementations that you can fill in later. We'll talk more about algorithm creation in the next tutorial. Next, let's talk about how to link to other libraries in your controller. These might be your own custom libraries or other libraries that you have from other vendors out there. The action scripts use what's called Makefile Project Creator under the hood. This is an open source project that you yourself can use to make your own projects if you like, but it helps to understand a little bit how it works in order to configure your GAMS generated project. Let's take a look at an actual project file called usingmadara.mpb, which should be in the source directory that you created. The includes line is what header files you need to include for your library to be useful to your GAMS controller. The second thing to look at here is the lib paths. This is the path to the libraries, whether they're DLL files, .so files for Linux, or things like that, where essentially your custom controller will be able to look to find it. This is essentially the LD library path in Linux. Libs is the name of the actual library that you're going to link to. This could be madara.so or madara.dll. You just need to add the actual library that you want to link to here. Modifying the project file is usually portable to all other operating systems, Linux, Windows, Mac OS, Android, things of that nature. So if you do this right, it should be portable to wherever you need to use it. We also include support for your own custom CPP and header files if you want to include those in your project. Let's take a look at the actual custom controller that was generated for you and explain the header file and source file inclusions. Essentially, if you need to add your own header files, such as export declarations or new classes that you'd like to declare, you put it in the header files section right here. If you need CPP files to be included, you put it in the source files. This is also where you can reference your custom libraries that you created earlier. Now that we've included our own custom header files and CPP files and maybe linked to new external libraries, let's go ahead and compile our new controller and run the simulation. The action script automates the compilation with a compile keyword, then launches vrep and starts the simulation for you. Try this yourself. Other notes on compilation. The project file can be modified to produce not only the custom controller that we default generate, but also your own libraries if you want to make a new library to include in other custom controllers. See the documentation for the Makefile Project Creator to see how to modify this file and workspace system for your own project needs. Users also have the option of creating their own make systems, but care should be taken to also include the ACE, Madara, and GAMS libraries if you want to use them in your project. The next steps in this tutorial series are to create our own distributed algorithm that we'll be able to simulate and watch work in our simulation environment.